Thank you for having me. It's been wonderful to be here. I understand that many of you are pursuing your studies. And so I thought that instead of just giving you just a normal talk, what I would do is to try to take you on an intellectual journey that my group and I have been walking through for the last few years and actually show you how our thinking, solving a problem, evolved over time, just to show you how, there is no single way, as they say, in a pretty scary way, they say in the United States, there is no single way to skin a cat. I'm not like to skin cats, but there are multiple ways in which apparently you can do it, and hopefully you'll see that. And any of you is familiar with this title, The Pit and the Pendulum? So this is actually a story from, assuming that this works, a story from, it's a horror story from Edgar Allan Poe. Okay, so the story goes as follows. We are during the Spanish Inquisition, and there is somebody that is tried by the Spanish Inquisition, is brought to trial, and is found guilty. And he loses his senses at the news. And when he wakes up, he's actually in a completely dark room. He realized that he's tied to a table in complete dark. And eventually, the only thing he can do is actually to hear this swoosh, swoosh, swoosh. And then he realizes that there is this pendulum that is hanging from the top. And at the end of the pendulum, there is a blade. And this blade is coming closer and closer and closer. And the reason that I'm telling you this story is because, believe it or not, I think there is a lot of similarity between that guy sitting right there and, of all people, database programmers. So database programmers, I feel, are also dealing with some kind of pendulum that is swinging over their head and sometimes inside their head between two seemingly irreconcilable goals. I guess I can't walk around very much. Two seemingly irreconcilable goals. On the one hand, ease of programming, and on the other hand, performance. It all started, on the side of ease of programming with the good old ACID guarantees that we're going to be talking about. But then people started to realize that they wanted more performance, and things started swinging on the other way. And they started swinging so much that people started to realize that perhaps we have performance, but we don't know anymore what we are programming. We don't know if our applications are correct or not. And so things started swinging in the other direction again. But that certainly doesn't make the life of our friend tied to the table any simpler. So what I would like to share with you today is what we have been trying to do in trying to see if there is a way to liberate that guy, to what degree we can liberate him or her from the table. And guilty. So what is the crux of the issue? The crux of the issue is that is what many of us have been battling against or enjoying living together, which is concurrency. Right? Concurrency is wonderful and is incredibly complex, can be incredibly complex as well. To give you an idea, here is a picture, a young girl on a balcony taken in 1911. It's called Venezia. Young girl on a balcony, and you can see the young girl on the balcony. And so the next picture instead, it's a painting of 1912, so 1 year later. And this is Carlo Carrà. It's called, actually, believe it or not, Concurrency, Woman on a Balcony. And you can see that you inject concurrency, and things become somewhat more complicated, right? More interesting, perhaps. You could say that it was fairly plain, the picture before. Now they're more interesting, but more complex. So one thing that, so you can see the tension, and there is no question that if you start easy, it's really nice to have the ACID guarantees that I assume you are familiar with when I mention the word ACID. And it is nice to know that all you need to do is to take your operation, wrap them inside a transaction, and suddenly you have the guarantee that either they all complete or none completes, that they are like diamonds, transactions are forever, and that, that when it comes to thinking about the correctness of your application, you can think about it on a per transaction basis. All you have to make sure is that your transaction is going to transition the system from a consistent state to another consistent state, independent on the fact that there are many other transactions running outside. So there is no question that ACID guarantees are great. The question is, can we afford them? And that's a question that actually the database community started struggling with fairly early. And what I would like to do, the first part of my talk, is actually going to try to take you through the evolution in thought that the community has had when it has come to try to formalize the notion of isolation, which is basically what defines what is visible from a transaction with respect to other concurrently executing transactions. So if you have perfectly isolated, you don't see anything when you're running concurrently with something else, but you can decide to be a little more lax in order to try to achieve more performance. It turns out that specifying, formalizing the notion of isolation is extremely tricky. And we're going to follow a little bit that evolution. And I'm going to end the first part of the talk by trying to make the case for a way to specify isolation properties that we have recently introduced that I personally find useful. And then in the second part of the talk, I'm going to try to go back to our friend on that table and try to see what we have been trying to do to free him. Okay? Great. So, the gold standard when it comes to isolation, this is not very useful. The gold standard when it comes to isolation is serializability, as you know. And in serializability, you would like to make sure that when you are running a bunch of transactions concurrently, there is actually one serial order of this transaction that is going to produce the same outcome that was produced by the concurrent execution of the transaction. But if you see a bunch of currently available database systems, you see that there are relatively few that, in fact, just two, that give you serializability as a default, and just few that actually can provide you serializability even at the strongest level of isolation that they are willing to provide. And the reason is that they're trying to achieve greater performance, and they think that serializability is a little too constraining. So there are some names here that you see, read, committed, snapshot, isolation. Let's try to understand what these things mean and how they were specified, these weaker notions. And to do that, I would like to take you back to 92 and to an attempt to specify in a standard way this weaker notion of isolation. This was an effort put together by ANSI, and the way in which they tried to describe weaker notion of isolation was as follows. They said, okay, if you are serializing, a transaction is completely isolated from other transactions. As you are weakening, what is going to happen is that there are going to be some phenomena that may show up that are weird and that wouldn't show up in serializability. And I'm going to consider weaker notion of isolation by considering how many of these weird phenomena I'm going to be allowing. Okay? So in, as you can see, there are going to be the weakest of these notions that they were defining, called read uncommitted, that was actually allowing all these three phenomena, which we are going to define: dirty read, fuzzy read, sometimes called repeatable read, and phantom reads, the phantom menace. And then as you were going down, you can see that as serializable, none of these bad events is allowed, and somewhere in between are the other ones. Let's actually look at what these phenomena actually mean. So dirty reads have their root in a write-read conflict. And here you can see what is going on. There is transaction 1 that is writing a value of A, and that value is actually read by transaction 2, right, before transaction 1 has committed. And now if transaction 1 aborts, transaction 2 has read a value and potentially written a value based on what it has read, based on a value that supposedly has never existed because, after all, transaction 1 aborted. So now the database reflects a state that was generated by an update that supposedly never occurred. No good. Okay? Those are dirty reads, and we don't like them. Something, a different kind of phenomenon that we would like to avoid is what are called fuzzy read or repeatable reads. Here is a situation in which you see that there is transaction 1 that reads the value of A. Transaction 2 concurrently writes the value of A. So far, so good. But unfortunately, transaction 1 reads again the value of A. And if they were fully isolated, it should see the same value the first time that it read and the second time that it read. But if they're not fully isolated, you may actually be able to see the value that transaction 2 had generated. Okay? And these are, if something like this happens, then you have a phenomenon that is called a non-repeatable read. Clear to everybody? Great. For the third example, this phantom example, it's basically non-repeatable reads, but on ranges of value as opposed to single values. So here is an example. Suppose that in the morning of July 10, 2018, you did a search on an SQL database that has the salaries of the player of Juventus, the Juventus soccer team, and you try to find what is the maximum salary. And it would turn out that it is 8 million euros. Okay? But if you do it a little later on July 10, some of you may know what happened on July 10, 2018. They actually acquired Ronaldo. You'll see that if you do another search, you see that, in fact, the maximum salary has suddenly become 30 million. Non-repeatable read, right? On a range, because you were doing actually a search for all the players of Juventus and try to find what was the maximum value. In that, you have injected a new value, and now you do read something different. Clear to everyone? Yes?
Maybe it's just a trivial question. So why do I want to read the same thing twice? Why can't I read it first time? I keep a local copy of it. I don't read from the database again. I just read my own.
You could, and that is what people sometimes do. But in this particular case, for whatever reason, they may want to say that it's fresher, or and it's a concern that they have. You could have you could have a different query and will have the same issue, right? Because you actually the query is different, but you are reading the same items in a slightly different queries, and you would like to have reads that are consistent between the two. Okay. Good. So the way in which ANSI SQL is defined is saying we want to eliminate these bad phenomena. And in serializability, there are no such bad phenomena. In the other intermediate levels, some of these may become visible. Okay? So the question is, so that sounds great. So what's not to like? And that's a question that actually good people like Berenson, Jim Gray, that some of you may have heard of, Phil Bernstein, that some of you may have heard of, asked themselves, and when they started looking at the ANSI standard, they said, no good. And no good for a number of reasons. The first, perhaps most fundamental one, is because that definition, they argue, Berenson, Gray, and Bernstein argue, is ambiguous. Let me try to show you in what sense they say it's ambiguous. Let's look, for instance, at something as simple as a dirty read. Remember the example that we saw before. If you look at the dirty read, there are actually two ways in which you can interpret what is being proscribed. You can have what they call a strict interpretation, in which you have X that is written by transaction 1 and read by transaction 2. And remember, transaction 1 aborts, and transaction 2 instead reflects the value that was written by an aborted transaction, bad. Right? But you can have a more expansive interpretation, in which you're not concerned about the fact that there has been an abort at the end. What you are concerned about is the root reason for this phenomenon, which was the write-read dependency between two transactions that have not yet committed. So in that more expansive interpretation, what you would have is you don't care whether transaction 1 committed or aborted. What you're not happy with is that there has been a write-read dependency between non-committed transactions. You with me? Great. So the question is, which one makes sense, right? It's ambiguous. What they actually point out is, well, let's try to analyze this a little bit. And one can do similar things for the other. So there are similar differences for the other anomalies that I was showing you before. So should we then focus on, if you want, the fact that there has been a failure, or on the fault that caused the failure, so to speak, if you want to have the traditional fault tolerance terminology. And the argument that they make is, look at these two transactions. If you look at these two transactions, there is a write-read dependency, and you can see that the first transaction is basically transferring 40, a value of 40 from the value from X to Y. You could even think of it as a transfer of money from account X to account Y. Initially, the value is 100. At the end of transaction 1, the value is 100. Transaction 2, you can think of it as running concurrently and trying to find what is the balance of X and Y. You should still find the balance to be 100, but if they are interleaving this way, it's not going to find the value to be 100, right? So that's a problem. And that's a problem that, so the execution is non-serializable. Now, if you take the restrictive view of these dirty reads, there is nothing wrong in this execution, right? Because none of the transactions has aborted. So there is nothing wrong. But if you take the expansive view, then, right? If you take instead the expansive view, you see that it violates the expansive view because it has this pattern of a write-read dependency between two transactions that haven't yet either committed or aborted. And it's actually a good thing, in a way, that, that the expansive view violates this, because if I stick by the expansive view, I'm going to refuse this particular execution. And that's a good thing, because I wouldn't want this execution because it violates invariance. So the argument that they make in their paper, and they build it up also for the other kind of anomalies that I was showing you before, is that, oh my goodness. I guess I'm going to show you another example. For non-repeatable reads, remember the business of non-repeatable reads? So here, again, I have a situation in which now it's T1 that is trying to produce the balance, and T2 that is doing the transfer. Yes? You with me? Now, if you look at this, it has at the core, it has this read-write dependency as opposed to write-read dependency. It has this read-write dependency that is at the core of the non-repeatable read issue. But no value here is actually being repeatedly read, right? So if you just take the narrow view of that, of the issue of non-repeatable read, you would be fine with this. While in fact, this is problematic. If you take instead the broader view, you would complain against this, and it would be good to complain against this. So again, they would argue that the approach that you would like to use is this broad interpretation that they call P2. They use P for the broad interpretation and A for the strict interpretation for anomaly and phenomenon that they're trying to prevent. And similarly, you can do the same kind of argument for the Ronaldo kind, the phantom reads that I was showing you before. So the first thing that Bernstein, Gray, et al. Point out is ANSI isolation level should be intended to prescribe phenomena, not anomaly. So it doesn't matter whether they abort or commit. if you have situation in which you have two transactions that have write-read, read-write dependencies, and they have not yet committed, you should just refuse, reject that. They should be proscribed. Okay. So what's not to like now, right? Well, they say, give me a moment, I'll tell you more. Yes.
Yeah. So I'm a little confused as to why the definitions have flowed out of the original descriptions like this. Because the original description just says that certain observations are possible or not possible. It doesn't say anything about dependencies between the original transactions and stuff. So I mean, what's not to like is sort of a very interpretable thing to say, right? I mean, it's fine that ANSI decided to sort of say something about observations of these programs, right? And just a way to interpret and say that if there are certain dependencies and something will be true.
So it's certainly true, and we are going to get to that. It's certainly true. I completely agree with you that what matters is what the different transactions observe. Yes. And instead, what is going on, as you can see, from the beginning of time, has been to define isolation guarantees in terms of relationship that exists between low-level read-write operations that take place. And what I'm going to try to argue towards the end, and I seem I have a friendly audience, is that that's not the right way to go. That the right way to go is to think about it in terms of states. Okay? But we are the first one to say that. Everybody has always said, no, 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 let's talk about it in terms of histories or low-level operations and the dependency between them. Okay, so another thing that they complain about is the way in which this ANSI scheme that I was describing before had emerged as a way to try to go beyond simply finding isolation level in terms of how the low-level locking mechanism that you will have inside the database actually function. We don't want to be able to say, I don't know, this level of isolation occurs because I take first this lock and then this other lock. There should be some higher level way to characterize what's going on that is not so mechanism driven. But in the process of doing that, Bernstein and Gray point out, the people that wrote out ANSI ended up coming up with something that is weaker than the original locking-based low-level definition we're achieving. And to point that out, here is how the locking specification of these isolation guarantees look like. As you can see, they say nothing about properties of operation or of execution. They only talk about how you acquire and release locks. Okay, so very, very mechanism-driven. But one of the things that they do, for instance, as you can see, is when it comes to, for instance, defining serializability in terms of locks, they maintain long locks, and by long-term locks, I mean locks that are acquired at the beginning of running a transaction and are released at the end of running a transaction, as opposed to short locks that are acquired at the beginning of an operation and released at the end of the operation. So if I look at serializability, you see that they have long write locks, fine, but they have long also read locks, which actually guarantee, if you take a long lock on a read, that guarantees that if you're doing those phantom, remember the phantom issues when we were inserting Ronaldo? Well, what they point out is, look, in reality, you're not just concerned about inserting Ronaldo. You're concerned also about deleting Ronaldo or updating Ronaldo. All of those things are avoided using locking serializable because you have these long-term locks. But if you look at the ANSI specification, they say nothing about deleting, inserting. Deleting, updating. They only talk about inserting. That's too narrow. So what they point out is when it comes to avoiding these phantom reads, which is this P3 property, they should prevent phantom that are due to deletion, updates, and additions, not just additions. Okay? Okay. Are they happy now? Gray et al. Yes, please.
So it seems to me that if you don't want serializability, then you should define the trade-off you want. you're really to give up serialization, you can should have some performance trade-off, and then you should design in such a way that it's not to implementation dependent. You understand it?
Well, if you say, I don't know what you mean by performance trade-off. What they do is they try to express which behavior that you didn't see when you were serializable, you are now going to be exposed to. And then there is going to be a payoff in terms of performance for being willing to have to go through the headaches of having that extra behavior visible to you. That's the approach that they use. Yes?
Just a comment about an analogy. So the computer architecture community has also kind of gone through this process. The issue between the A and the B seems to be which states will be exposed. One of them says that this is completely disallowed, and in the other one you say that I can expose this state provided it is eventually going to be work.
Right. So and there is an analogous in this discussion. So it's actually a very good. It's a very good observation that you're raising. So again, we are still with our friend Gray and Bernstein, and so again, they are really nice people, but they keep complaining. So here they say, well, you know, it's all good, but it's still too weak. Even after we do these fixes, it's still too weak. And to see why it's too weak, let me show you the two ways in which things where this intermediate isolation level were specified. This is the ANSI way. This is just the lock-based way, right? Now, if you look at read uncommitted says dirty reads are permitted, fuzzy reads are permitted, phantom reads are permitted. In fact, everything is permitted. But if you look at what's going on instead on the locking side, you see that not exactly everything is permitted. And the reason is that you are keeping these long write locks, which means that once a transaction starts and it performs a write, it's going to acquire the lock on the write, and no other transaction is going to be able, that runs concurrently, is going to be able to conflict with another write with the write of the transaction that has acquired the lock. So the fact that there are no write-write conflicts is not captured in ANSI, but is instead captured with the lock specification. So what our friends then point out is, I don't want to have what they call dirty writes, when you have write-write conflict. So I should introduce another of these phenomena that I want to avoid that they call P0. And P0 is a phenomenon that is basically characterized by the fact that there is a write-write conflict between operational transactions that have not committed. Okay? So now they're finally, we got these guys off our back. They're happy. Okay? So they are happy, and they come with a definition that looks like this, that sort of summarizes what we talked about. They're happy, but it's not really sunny yet outside, despite the fact that it's always sunny here. The criticism that they got immediately is, yes, fine, you have been able to save all these things, fix all these things, but if you now look at your definition, P0, P1, P2, P3, they're just locks. Your definition is, in fact, you brought it back to be totally lock-centric, right? So what you have defined, you have given it fancy names, but it's just a disguised way to just describe how the locking mechanisms work. And furthermore, it's overly restrictive, as you were pointing out. For instance, consider P0, the dirty writes that I was describing. P0 says, if a transaction writes on X, another concurrent transaction should not be writing on X as well. That seems overly strong. All I have to make sure is to guarantee that if a transaction writes on X and another transaction concurrently writes on X, not both can commit. Right? So I could, if I want to use an optimistic approach to concurrency control in which I let transaction execute as they want, and at the end I check whether there is a conflict, that kind of methodology is actually ruled out by that formalization that I showed you. But in practice, I would like to be able to express it, right? I would like my isolation guarantee to be able to account for optimistic implementation, or for those of you who know what I'm talking about, multi-version implementation, nothing that the previous spec was able to do. And fundamentally, if you think about it, the reason why it feels over-restrictive is because, yeah, there's the rub, is because what the previous formalization was trying to do was to express isolation property that involve potentially what is happening in concurrently to multiple variables. Remember, for instance, maintaining invariance, right? By simply constraining what happens on just one of those, to just one of those variables. And instead, you have, what you're trying to do is actually maintain properties that capture the relationship between variables. Oh, this may work better. That capture the relationship between variables and, oh, I have to. Too much. Okay, maybe I can try. Thank you. Okay, so far so good. So let's see if this works better. Can try. Okay, and another thing is, which is sort of connected. If you look at those specifications make no difference between what they ask of transactions that are going to commit and what they ask of transactions in general, right? But if you look at optimistic techniques, as we were discussing a moment ago, they thrive on the fact that their requirements about transactions differ as to whether the transaction commit or it doesn't. They don't have a very strict requirement on transaction in general. It's only when they are asked, can they commit or not, that they become demanding and say, no, sorry, you can't commit because blah, 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 blah. Right? You with me? This actually, I was too far away. And again, they don't account for multi-version system. And just to give you a sense of the kind of things that you may deal with, the kind of isolation guarantees you may deal with in a multi-version mechanism, in a multi-version environment, let me introduce to you to the notion of snapshot isolation. I don't know if are you familiar with the notion of snapshot isolation? Okay, so the idea of snapshot isolation is simple. When a transaction starts, what it does, it reads the state of the database in a snapshot. Okay, so it sort of takes a snapshot of the database when it reads. And then as it executes, it sort of updates its local copy of the state. And when it's about to commit, what it's going to look is verify whether the objects that that transaction has changed as it was executing are at all conflicting with objects that have changed in the database since the snapshot was taken. If there is a conflict, then the new transaction shouldn't commit. If there is no conflict, then it can commit. Okay? So this sounds remarkably similar to, at first blush, may sound remarkably similar to what serializability to some degree gives you, except that there is an issue that can come up with snapshot isolation that doesn't come up with serializability. And the problem is known as right skew. Let me show you what right skew looks like. Here is a transaction, and transaction 1 is going to take this database that has this ball of different colors, and is going to change all the green balls to red. Okay? And transaction 2 is going to change all the red balls to green. So transaction 1 is then going to perform this change, right? And transaction 2 is going to perform this change. Now let's look at the objects that have been changed by the two transactions. The objects that have been changed by the top transaction are the one with the star. The objects that have been changed by the bottom transaction are also the one with the star. As you can see, there is no conflict. So when they come together, they're actually going to produce this state. And this state is, of course, a state that couldn't have been produced if the two transactions had been serialized. Because if they had been serialized, either everything would be red or everything would be green, right? Great. So we had to wait until 99 when Atul Adya, now I think, is he still at Microsoft? Okay. Huh? Google now. Okay. There you go, the Game of Thrones. So when Atul Adya and her advisor, Barbara Liskov, came up with the first truly general and elegant and beautiful formalization of isolation guarantees. And it's still defined in terms of histories of low-level operations. Okay? Still a relationship between histories of operation. There is a partial order of the read-write operation that occur in the different transactions, and then there is a total order of the version of objects that are generated as the execution proceeds. And correctness guarantees are expressed in terms of what they call a serialization graph, a direct serialization graph that contains as nodes transactions that have committed and has edges that connect transactions that have dependencies between them. And there are, as you can see, there are read-write dependency, write-write dependency, write-read dependency. Some read-write dependency are called anti-dependencies for reasons that we are not going to get into. And there are even, in order to capture things like snapshot isolation, there are even more edges that are introduced that have some notion of time, these S edges. This, if there is an edge between Ti and Tj with an S on top, it means that Ti has committed before Tj started. Okay? Good. And let me show you what is the beauty of this. You may remember that if I was looking at read uncommitted, the weakest of all possible weaker notion of isolation, it still was preventing dirty writes, right? And we saw that one problem with the old definition of preventing dirty writes, it was that it was ruling out optimistic implementations, right? In which you allow the writes to go on. It's only at the time of commit that you kill potentially a transaction that is creating trouble. And now, if you look at read uncommitted here, again, the old way was this. In the new way, in the Adya-Liskov way, instead they have a new, instead of P0, they call it G0 for general. And they say what you should do is to ensure that your dependency graph, your direct serialization graph, is actually not going to contain cycles that contain write-write edges. Now, remember that the nodes in that graph are only committed transactions. So what it says is that you cannot have cycles between committed transactions, which is what you want. But it doesn't say anything about what's going on before. The transaction can have conflicting writes as long as both of them don't turn out to be nodes in my serialization graph, right? And it would be fun, and this is the part that I had to cut when we found out that it's only an hour and a half instead of 2 hours. But it would be fun to go over the other ones to see how actually insightful and powerful this notion is. If it comes to stronger isolation level, in a nutshell, they basically want to ensure that there are no aborted reads, no intermediate reads, and then they have a notion of non-circularity. And the notion of non-circularity that we saw before, it was a non-circularity that involved only write-write edges. If you consider different level of isolation, the edges that are involved in the non-circularity are going to be different. And the requirements that you're going to have are going to be more complex in order to be able to express this other level of isolation that I was describing before. To give you a sense how things can get, this is, for instance, what snapshot isolation says. So you shouldn't have the first kind of graph, the second kind of graph, the third kind of graph. It gets pretty hairy, but it's general, it's implementation independent, it's precise. But as you can see, now think about it as being somebody who has actually to work as an application developer to try to understand what these isolation properties are all about. And I tell you, oh, easy, you want snapshot isolation. All you have, see, that's the graphs that shouldn't occur. And by the way, these operations that you see, this read-write dependency, write-write dependency, if what you're trying to do is to run a database, your application, a remote database, you have no control over these low-level operations. These low-level operations are occurring somewhere inside the system that you don't know, and somehow I'm asking you to instead found your understanding of the properties that you're going to get as an application developer in terms of fairly obscure graphs that are expressing a relationship between operations that are invisible to you. That's not perhaps the most intuitive way to convey what the properties are trying to convey. And so despite the fact that this is a beautiful piece of work, all is well. So for instance, if you look at execution like this, let me show you the state of confusion in which we are. And this is the state of confusion that applies even just to serializability, okay, which is the easiest that everybody should understand. You look at an execution, a potential trace like this, and you ask yourself, is this a serializable trace or not? It is a serializable trace, despite the fact that there are these write-write conflicts. All you have to do is basically reorder the writes that you can do because there are no intermediate reads that force dependencies, and it should be serializable. But if you ask these systems whether it is serializable or not, this system all claim to provide serializability. Some say yes, some say no. And if you look at an execution like this execution is actually not serializable. Okay? And if you ask our friendly system, is this okay? Serializable system, are you going to accept this schedule? Some say yes, and some say no. I would argue that part of the confusion that becomes even larger if you consider things like snapshot isolation, to give you a sense, there have been no fewer than 10 or 12 different snapshot isolation flavors that have been introduced that are actually different with respect to one another in terms of the mechanism that they use to decide where to assign the timestamp to the operation that, remember that there is a start time and a commit time. They use different mechanism in doing that, and they define different isolation levels. And because their definition are so tied to the implementation, is very different to be able to compare what is the relative power of this notion of isolation, right? You have no idea.
Lorenzo,
yes?
in this example on the slide, you're basically showing that these three tools are all incorrect.
I'm trying to show you that there is enough confusion in the reality.
Tool to check serializability that is generally
These are real databases. And what I was trying to convey is that if you are a user and you go to Oracle 12c, and Oracle 12c says, we are a serializable database, you would expect that execution like the one on the right would not be allowed by 12c. And so you don't worry about something like that happening, and instead it does happen.
What you're showing is that these tools are actually providing us incorrect information.
And I'm arguing that the reason for that is not that because these are lousy people, but because, at least in part, the formalism that they were supposed to rely upon in order to be precise is sufficiently confusing that it becomes hard, even for people as professional as Oracle, to actually get it right.
Related to that, I mean, if the output goal is to get serializability, and you will say, I don't care about all the specifications, security specifications, I will just get this implementation and do a proof showing that it preserves serializability in all cases. And would that solve?
Well, remember that these are real systems, so they don't, they are interested in providing whatever guarantees they want to provide, and at the same time, they want people to use them, so they have to give you performance as well. And so they are trying to be overly clever beyond their, what is wise for them.
But they claim they provide serialization.
They claim that they provide
They
serialization.
don't provide a proof, and
No, they don't provide a proof. But you are a user. There are relative, maybe everybody knows is different, but most users out there, if they are given Oracle 12c that says, this is a serializable system, they're not going to say, well, I don't believe you. Show me the proof. They're just going to say, oh, this is a serializable system, okay? So I'm going to claim that the reason for the confusion is that there exists, in my view, and apparently in Pratik's view, a semantic gap between how isolation properties are formalized and how actually applications perceive, experience this isolation property. I'm going to claim that although all formalizations are based on these histories of invisible operations, the reality for users of isolation guarantees is that they perceive them as basically contracts between the system and them that specify what kind of states they are going to be allowed to observe. Right? The isolation says what you are going to be able to see, what is allowed, what can be seen. And so what we proposed to do, and we had a paper last year in POTSI, what we proposed to do was actually to do precisely that, to try to ask ourselves, can we build a formalization of isolation properties that is purely based on states, so that it is actually close to the experience that applications have? Because what applications do is, to them, the database is sort of a black box that periodically sort of turns on the light, you're seeing some states, and then the the black box keeps executing. You don't see what's inside the black box. You just see the states. So the way in which we are going to do it, we did it, was to define isolation properties as constraints on what we call read states. And this is something that perhaps is going to, at least in my mind, resonates a little bit with things that hopefully you like, Yoram. So these read states are states that are consistent with what an application may have observed. So for instance, suppose that there are these 3 states that exist at some point in the system. Then if I'm executing an operation that returns the value y0, I'm going to say that the read state for this operation is just the first state. Right? And if instead I have an operation that is actually going to return z1, right? Then there are multiple possible worlds that are actually consistent with this operation. So one way to look at what read states do is actually they do something similar to Kripke structures. They sort of capture the set of possible worlds that are consistent with the observation that a transaction makes as it executes. Okay? And then what I'm going to do is at commit time, I'm going to apply a commit test that is going to narrow down among all the set of possible states, the states that are consistent with the isolation constraint that I have. And if, as a result of that narrow down, my set of read state is empty, then the isolation property doesn't hold. Otherwise, it holds. As simple as that. Right, which is exactly what I wrote here. So I just want to give you a sense of how this is done, just for 2 notions of isolation. Serializability, because it's our friend, and snapshot isolation, because you saw how complicated it is. So for serializability, to do that, I'm going to introduce 2 notions, a notion of what I call a parent state and a complete state. So a parent state, if this is execution, and this is, this SE is the set of states that are totally ordered by that order that defined 30, 0, then T2, than T, I'm going to say that the parent state of T here is the state from which T commits. Okay? So it's the state that precedes it in the total order. So in this particular case, this would be the parent state of T. Clear to everybody? And then I'm going to say that a state is complete for T if that state satisfies, so from that state, I can satisfy all the values that have been observed by all the operation inside that transaction. So then I'm going to say that that state is complete for that transaction. So from that, I can just read from that state, and I can satisfy everything that the transaction has observed. So for instance, if I am in a situation like this, and my transaction reads and observes Z1, T observes Z1, then these are potential read states, right? For Y1, this is the only read state. And if I look at that state in the middle, you see that is actually, if these are the only two operations in transaction T, this is a complete state for that transaction. You with me? Great. So now I can define serializability. And serializability is simply going to say, oh, what happened? Sorry, I must have touched something. Okay, serializability. And serializability is simply going to say the following. Given a set of transaction T and their read state, serializability holds if there is an execution E such that for all the transactions in this set of transactions, the following is true. The parent state of the transaction is complete. That's it. Basically, an execution is serializable if the state from which I'm committing is a complete state for me. I can just attach myself to it, and I'm able to perform correctly all the reads that I need to perform. Completely trivial. Huh? And that's it. All I need to guarantee is that the parent state is a complete state for the transaction, and that gives me serializability. Now let's look at snapshot isolation. Snapshot isolation is a tougher cookie. Remember, it is a tougher cookie, right? So let's look what we need. So this is the same, right? Given blah, 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 blah. So what is the condition? This is going to be the commit condition that I have to express. The first thing that I'm going to say is I want to require that there exists a complete state for the transaction. But it doesn't necessarily have to be the parent state. Any state that precedes, that is complete, is good enough to serve as the snapshot state. So there must exist a complete snapshot state, requirement number one, which I can just express like this. Right? So there is a state that precedes, that is complete. And then what? Remember that what I need to require is that if I consider the updates that the transaction has performed and the updates that have occurred in the execution since my snapshot, there are no conflicts. Okay? So let's say that I'm expressing this as this delta SSP is the set of things that have changed since the snapshot state S until my parent state. So the things basically that occurred in the execution up to now. So if I look at the things that have changed, and I take the intersection of the things that have changed with the things that I've changed, that intersection should be empty. That's snapshot isolation. I would humbly submit that is easier to understand than what you've seen before. And the good news is that we can do this for all the properties that you have seen, the weaker isolation properties that you have seen before. And furthermore, those of you who worked with formalism know that good formalism is not just interesting because it's aesthetically pleasing, but because there are good things that you can do with good formalism that you can't quite do with less good formalism. So for instance, one thing that we were able to do was to show that once you take those 10 notions of snapshot isolation that I was describing, or 12 that I was describing before, and you express them in terms of states, you suddenly realize that a bunch of things that have been published are actually expressing exactly the same thing. And furthermore, you can actually show that of the things that are different, it's very easy to actually put them in some kind of hierarchy that actually expresses the relative power that they have, something that was impossible before. Another thing that it allows you to do, because it frees you from low-level details, it actually allows you to start thinking potentially at different implementations that capture the spec and are less tied to the low-level detail. And in an NSTI paper that we published last year, which showed exactly how this kind of spec guided us to a new, more scalable implementation of something that is called parallel snapshot isolation that people were excited about. Okay? So that's the first part of my talk. And I already am going to warn you that it looks like I may go by about 5 minutes, and I apologize for that. So we saw all of this different, this weaker notion of isolation that have sort of taken our pendulum and have started swifting the pendulum on the other side. But the worst thing that if you want to create havoc, the best thing to do is to leave it to systems people. This was all the damage that database people would be able to do, but systems people can do much worse. And this is exactly what systems people did when they introduced this notion of base. Base stands for supposedly basically available, soft state, eventually consistent. But it's really just something to say we are geeks and we want to say this is not acid, so it's going to be base. And the notion of base is very simple. Remember your good acid storage transactional guarantee, right? Beautiful. It would be a real pity if something bad were to happen to it. I can say that as an Italian. And sure enough, you take acid storage and you just blow it out. And all those guarantees, you blow them out. And instead, you consider a much simpler storage interface that is based simply on put and get operation. And all the management of concurrency that was performed for you, all that complexity, you are actually going to give to the strong, powerful application programmers who now have the responsibility of taking care of all of that. The hope is that they're going to be able to squeeze every possible ounce of performance by moving everything at the application level. The concern, as you can imagine, is that now they actually have to start reasoning about what happens when there are all these interleaving between operations that before were taken care for them. And so these things actually grow, the number of interleavings that you have to think about grows exponentially. And so, complexity goes way on the other side. Right? And so that actually leads us back to our friend here. And so what I would like to do is to tell you then what we try to do in order to address this. It seems, when we started looking at it, it seems like a pretty tough nut to crack. And the reason, fundamentally, is that if you're trying to achieve more performance, what you want is more concurrency, right? And so, for instance, you could imagine here I have a transaction that performs a transfer. And if I want to achieve more performance, what I could say is, you know what, I'm going to take this transaction and I'm going to chop it. I'm going to chop it in 2 parts. And now I'm going to be able to actually run these 2 parts somehow concurrently, right? So instead of running an execution like this, I'm going to be able to at least partially overlap executions. Oops, yes, partial, yeah, doesn't. And as you can see, it doesn't look that great because it sounds okay until you realize that there are other transactions that may actually now be able to see that intermediate state that wasn't visible before when the transaction was just a single one. But now that you have chopped it, there is this intermediate state that has become visible. And you have to worry whether that violates anything that you care about. For instance, here when we were doing the transfer, the balance operation before was either going to see things that had happened before the transfer or after the transfer. Life was good. But if I'm chopping, what may happen is something like this, right? Which actually allows the balance to see an intermediate state that it wasn't supposed to see, and suddenly I get the wrong balance. And what is really scary about this, if you extrapolate about what's going on, is that this suggests that every time I'm changing even just one transaction, in just introducing one extra possibility for interleaving, that actually may require me to have to think about the implication on all the other transactions that I have in the system. And you can see the complexity gets out of control, right? So it seems that in a way, the wall that we have to face is a pretty fundamental wall, because if I want to have better performance, I have to allow for more interleavings. But if I allow for more interleavings, then there is more complexity that I have to worry about. So that was the situation in which we found ourselves when we started digging in this direction. And that's when we decided to turn to this man. He has a few interesting features. He has a nice beard, which is always impressive. And another very important feature is that he's Italian. His name is, you know him, even if you don't know him. His name is Vilfredo Pareto, right? Of Pareto principle fame and Pareto optimality. And so what does Vilfredo Pareto, what does he has to say to us? As you may know, there is such a thing called the Pareto principle that says if you consider a complex system, it's not the case that every possible cause is actually responsible for, in equal terms, for all the behaviors of this system. Things are actually non-uniform. Typically, very few causes are responsible for the overwhelming majority of the effects. Pareto called it the 20-80 rule. In software, we even have the 90-10 rule, right? Which is basically saying something along the same lines. And we actually decided to purely empirically try to find out whether this Pareto principle held also in these database applications that we were dealing with. Namely, is it the case that applications that are too performance constrained when living inside the ACID world, is it because they sort of burst, they want more performance across the board, or is it more limited, the demand for performance, to just a few transactions? And the answer is, guess what? Just a few, right? So in fact, if you consider these applications, and we surveyed quite a few, you're going to find out that not all transactions are created equal. Some transactions are performance critical, but the overwhelming number of transactions are not. And they're not either because they are lightweight, or because they run very seldom, or because of a number of other reasons. Okay? So if you now take this observation and you try to see where it leaves us, it actually potentially leaves us in an even, at first blush, in an even worse place. Because remember what I was arguing before, that performance requires interleaving, interleaving requires complexity. Well, it's actually worse in a way, because what Pareto says is interleavings always give you complexity, but only seldom give you performance, right? So whenever you are providing extra interleaving, you're guaranteed that there is going to be more complexity, but whether at least you're going to get some payoff in performance is unclear, because in a lot of cases, you're going to provide extra interleaving for transactions that don't care, they don't matter. But if you take that and you flip it, that actually gives you an opportunity. Because The observation then could be, well, suppose that instead of just allowing more interleavings, I were to be able to allow for more interleavings selectively, so that these extra interleavings are not visible to everyone. They're only visible to those transactions that can actually gain performance benefit out of them. Then the hope is that I'm going to be able to get most of the performance that I would have been able to get if I allowed them to be visible to everybody, but at a fraction of the complexity, because I don't have to reason about all of the transactions that don't see these extra interleaving. And that led us to build in the first system that I want to talk to you about is a system that, because if you guys are geeks, we are willing to fight with anybody, that we call SALT. And perhaps you can see why we called it SALT, because if you take an acid and a base and you put them together, okay, fine. SALT tries to solve this problem by starting from the observation that not all transactions are created equal. And so if not all transactions are created equal, maybe it's worthwhile to define an abstraction that is dedicated to those few transactions that are performance critical transactions. Okay? So I'm going to have a transactional abstraction that is going to be specialized for those performance critical transactions. And the other transactions instead that are not performance critical, they're just going to be left alone. And I have to find a way in which these two different kinds of transaction can sing together kumbaya inside the same database. Okay? So the idea behind this is then to introduce what we call a base transaction. That's the abstraction that we introduce. And a base transaction is built by taking one of your performance critical acid transaction and massaging. How do we massage it? We recognize that inside this base transaction, inside this transaction, there is some structure. And that structure is going to be expressed as looking at the transaction as a sequence of mini transactions, which, because we were on a chemically induced stupor, we called alkaline transactions. Sorry, I know, bad word. We just got so excited. So you can think you have this acid transaction and you split it in a sequence of alkaline transactions, okay? And then you wrap this whole thing into something that we are going to call a base transaction. So what is good about base transactions? What is good about them is that on the one hand, base transactions provide you atomicity and durability at the same granularity as the acid transaction that they started with. So either all these alkaline transactions commit or none commit. Right? And then when they are durable, either they're all durable or none is durable. But when it comes to, one of the things that are great about transaction is that they take these four properties, the acid property, and they give them to you in little bricks, all of the same size. But if you have done Lego, you know that sometimes it's nice to have smaller bricks. They're still Lego, but they're smaller. And here we want to provide you, when it comes to isolation, flexibility in terms of the granularity at which we are going to present isolation. In particular, base transactions are going to provide different isolation guarantees for different type of transactions. A way to understand, perhaps intuitively, how this isolation mechanism that we put in place, the isolation policy that we put in place that we call salt isolation, the way in which it works is similar to this picture. Look at this picture. If you look at this picture, you look at it and you turn your head one way, it's going to look like a duck. And if you turn your head the other way, it looks like a rabbit, right? And so salt isolation makes base transaction look sometimes to somebody as ducks, to somebody as rabbits. So base transaction look to other base transaction. So a base transaction looks to another base transaction or to another instance of the same base transaction as a sequence of alkaline transactions. And so they can interleave with one another at the granularity of alkaline transactions. But a base transaction looks to a non-performance critical acid transaction just like a good old acid transaction. No difference. So all the large majority of acid transactions see no extra additional interleaving. Okay? Okay, good. Right. So in other words, if base interacts with base, I can have interleavings like this. If base interacts with acid transaction, then the only states that acid transaction can see are the same state as they always saw. So how well does something like this work in practice? There are many questions that you can ask. From our perspective, what we wanted to see was how does the performance of something like salt compares with the performance that I can get in an acid environment. So to do that, we went inside. When I say we, this is the royal we. In reality, it's my courageous students. Went inside my SQL cluster and got into the guts of my SQL cluster, ripped the concurrency control in my SQL cluster, and implemented salt isolation inside my SQL cluster. And then they started to run side by side to see what you could do. And the other thing is, of course, it's not just performance. The question is, how much work is it required to be able to achieve whatever level of performance we are able to achieve? Because remember, the goal, the hope is that we're going to be able to get most of the performance with a modicum of complexity. And one way to measure that complexity would be to say, how many transactions do I actually need to basify in order to be able to get benefit? And in fact, how much benefit do I get by only basifying very, 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 very few? Right. So here are a couple of graphs that I'm going to show you, because in the interest of time, I'm not going to go incredibly deep in all of this, but I want to give you a sense. So these are two applications. One is good old TPCC, that is sort of the standard way in which database people measure their performance. And another one is an application called Fusion Ticket, which is an online ticket distributing application, which is much larger in terms of transaction than TPCC. And as you can see, there is a fairly substantial improvement. This is a latency throughput graph. So when you see that the line starts pointing up, is because the system has become overloaded. And so adding more load only increases latency and doesn't increase throughput at all. Okay? So and you can see that we get to that saturation point much later. There is over a factor of 6 that we are getting from this. And if you ask yourself, what kind of complexity is it involved in getting these kind of results, it turns out that this shows you when it comes to TPCC, we basically had to, and we compared that with the performance that you would get if you were to basify the whole thing. Okay? And you can see that with TPCC, basifying just a couple of transactions gets you very much along the way. Basifying 3 transactions gets you pretty much all the way. When it comes instead to Fusion Ticket was a very large system with dozens of transactions. Every time that you're basifying a transaction, you have to start thinking about those pesky interleavings. And so it was becoming increasingly complicated to keep on basifying. We had, a fairly significant jump just by basifying one thing. The question is, how much are we leaving on the table? To get that answer, what we did was to actually take the application and just chop it in individual operations without worrying at all about correctness. That would give us an upper bound on the performance that we can possibly hope to be able to get. Right? Because we don't care about correctness, we just want to be fast. And as you can see, if we do that, if we just chop at the level of raw operation, we get a boost of 7.2 times, and just by basifying one transaction, we get a 6.5 times. That's pretty good. There was a question.
When you say specifying, you mean modify the SQL or you mean something else?
I mean working inside the transaction, no SQL, working inside the transaction and restructuring that transaction so that it would actually perform, could be expressed in terms of these mini acid. It's certainly true that we had to go inside. For instance, we went inside TPCC, and that bench. We just reordered the operation inside TPCC. The transactions are the same. We just reorder them. Okay. It is, because we are running. So the outside benchmark is exactly the same. The invocation is exactly the same. What we have done is just reorder the operation. Yes. Correct. They were not, TPCC is not incredibly complex. I can't remember how many operations are inside, and I would have to refer you back to the paper for that, and I apologize for that. What I'd like to tell you, though, is that when we had these results, which we presented a few years ago at, I don't remember if it was SOSP or SDI, when we had these results, we sort of felt pretty good. Right? And I started, going around, and I kind of thought, well, maybe we haven't quite destroyed the pendulum, but we created a little bit of damage. So I would go to give a talk, and people would say, this is great. But those transactions that you are basifying, just like you guys were about to say, those transactions that you're basifying, how do you go about basifying those transactions, right? What is, is there some automatic way to basify? And I would say, no, there isn't an automatic way. When you go inside basifying a transaction, you have the challenge that everybody that tried to take an acid system and transform it into a base system had to face, except that you have to face it only for 1, 2, 3 transactions. They have to face it for all the transactions. Isn't that great? And they would say, yep, that's great, but how do you basify those transactions? So it seems that, despite whatever we were trying to gain, programming-based transaction is still not trivial, right? And so we started to ask ourselves, what do these people want? We had the feeling that they were trying to send us a message, that they wanted us to do something, and we couldn't quite understand what they wanted. And then it sort of dawned on us. What application programmers really want is ACID transactions. We were just trying to find the sweet spot between acid and base. And what people were telling us is, sorry, if you move outside of acid, there is no sweet. It's only sour. There is no sweet spot. And so that's when we decided to revisit the way in which we were going about trying to solve this problem. And we decided to say, well, if everybody likes acid, we are going to embrace acid. We are just going to try to provide programmers with the same uniform abstraction, the acid abstraction that they are familiar with. What we're going to try to do, though, is to try to implement it in a slightly more performant way. And the way in which we went about this was, again, by starting from the observation that not all transactions are created equal. And before, what we had derived from this observation was that we should use a flexible abstraction. And as we said, instead, we don't want to use a flexible abstraction anymore. We want to provide a uniform abstraction. So what is the only other thing that we can do? Well, if we don't want to change the abstraction, the only thing that you can do is to specialize the implementation of that abstraction. And which is, admittedly, what we ended up doing in a system that we called CALAS. And if you don't know who that lady is, you owe it to yourself to find out who she is. Okay? It also happens, for those of you who may find this amusing, that Callas turns out the most popular brand of salt in Greece. So there is also that connection in addition to, yeah, pretty neat. Right? So just like Callas, we want to make sure that it's going to, provide the same abstraction, but, in a multiplicity of different implementation of that abstraction. And the observation that we are making is when it comes to uniformity, uniformity is really good if you're thinking about abstractions, because it limits the kind of things that you have to think about, right? But uniformity, when it comes to mechanism, basically means having to settle for one-size-fits-all kind of solution. If you think about each of the concurrency control mechanisms that you can study in the literature, you find out that they are really good in certain settings, but they are weaker in other settings, and vice versa, right? And if you focus on a single mechanism, you have this one-size-fits-all kind of attitude that it's fine, but it's certainly not going to be the most conducive performance. You're leaving some performance on the table. So our idea then was to do something that we have been told it's a good thing to do since we have been in graduate school, or perhaps before here at NUS. Namely, that it's good to decouple abstraction from implementation. And we do that by introducing a new concurrency control, a new approach to concurrency control that we call modular concurrency control. And the idea of modular concurrency control is the following. We're going to take our transactions, and we are going to partition the set of transactions in groups. Okay? And what we are going to do is actually associate with each group a concurrency control mechanism that is going to be specialized for the transaction inside that group. Because it only has to work with the transaction inside that group, can be significantly more aggressive than a mechanism that would have to work for all transactions. Right? If you go and watch movies with your best friend, and you both are crazy about, I don't know, science fiction, you can probably go to much more deep science fiction movie than if you have to go out with everybody in this room. I would say, I hate science fiction. But so there are going to be specialized in-group concurrency control that are going to be very aggressive. Of course, there are going to be that are going to manage conflict between the transaction within each group. Of course, there are going to be conflicts that are going to be across groups, and there is going to be a cross-group concurrency control that is going to manage conflicts that occur across these different groups. And that is actually going to give us another thing that we have been told since we were little that is a good thing, which is separation of concerns. When reasoning about the correctness of the concurrency control for one particular group, you have to worry not at all about whatever concurrency control other groups are implementing for themselves. Okay? You can just think in isolation about correctness within each group. And again, the intuition for why this is a good idea is because by specializing things within one group, we can be more aggressive and achieve more powerful optimization. Okay, I'm just thinking about what lies ahead, and I don't want to impose on you guys. So I'm thinking maybe I'm just going to. So the next thing that I would have to do, of course, is to show you that something like this is correct. That I can pull correctness off. And when it comes to try to pull correctness off, it seems that the goal would be that there should be no, and here I'm going to express it in the terminology that Alia and Liskov would have expressed, because this is older work. I want to make sure that if you look at that graph, remember the dependency graph, there should be no cycle across the entire graph. And I'm going to try to argue that by arguing that there are going to be no cycles within each group, and then there are going to be no cycles that span multiple groups. Okay? And the first thing that I'm going to try to show is that there are going to be no cycles that span multiple groups under the assumption that there are no cycles within each group. Okay? So the mechanism that we're going to use to achieve that result is a mechanism that, for historical reason, we call nexus locks. So what are these nexus locks? You have to think as nexus locks as locks that are ubiquitous. Every time one touches a variable for either reading or writing, it acquires one of these nexus locks. But these nexus locks, a little bit like salt, have a they have different behaviors depending who invokes them. In particular, if there are operations that are conflicting, namely they're not both read operations, and these operations are invoked by transactions that are in different groups, nexus locks behave just like locks. They stop you. But if these operations are within the same group, nexus locks are permissive. They actually allow even operations that are conflicting to go ahead, despite the fact that there are these nexus locks. And it better be like that, because remember, this is the cross-group mechanism. And the goal of the cross-group mechanism is to give me correctness and not stand in the way of performance. And if I made these nexus lock interfere with what happens inside each group, then the performance would go out of the window. Yes? So this is great, except that it doesn't work. And to show you that it doesn't work, let me show you an example that shows that it doesn't work. Here I have a transaction that is in a group, and this transaction first touches variable A and acquires the nexus lock on variable A. And then there is another transaction that also wants to write A. Because they are in the same group, it's going to acquire the nexus lock as well. They are going to conflict, but no problem because we are in the same group. Right? And there is going to be a dependency that is going to be generated between T1 and T2. Right? Now, suppose that T2 does its beautiful work, and then at some point commits. And when it commits, it releases its locks. Now, there is another transaction, transaction 3, that is in a different group. And this transaction is going to acquire the lock on B, which it can because transaction 2 that had it has released it. Right? And there is a dependency that is going to be generated. And then transaction 3 is going to touch some other object, and then is going to commit and release. And now you see what I'm going to do. Right? What I'm going to do, which is pretty sad, I'm going to let transaction 1 now touch C, and there is going to be a cycle that is going to be generated. And that's not good. Right? And we allow that. That's not good. So when we observe this, we ask ourselves, wait a second, how come that doesn't happen with traditional locking? How did we get into this mess? And if you think about it, it's because in traditional locking ties depends on to complete before. So T2 is not allowed to start until T1 completes. Right? And then there cannot be cycles because completes before cannot be cyclic. And so depends on cannot be cyclic. So if T2 depends on T1, T2 cannot start until T1 is finished. That's what happened in traditional locks. And so you have something like this. Right? And then there is no problem. Right? Except that, of course, this is serializing the execution, which means taking performance and say, ciao, ciao. Right? So if you look at where we were, you can see that in our case, this business of tying dependency and finishing before only applies for transactions that are in different groups, but it doesn't apply two transactions that are in the same group, and again, for good reason, because we don't want to serialize the transaction within a single group, or otherwise, no performance. The way to get around this was to actually refine the condition that traditional locking enforces. Traditional locking says if T2 depends on T1, T2 cannot start before T1 completes. We refine that condition by saying if T2 depends on T1, T2 cannot release its nexus lock until T1 releases its nexus lock. It can release any other lock, any resources it is holding when it commits, but it should keep on the nexus lock. So doing that actually leads to the following. Instead of having something like this, you are allowing this kind of execution, except that when T2 here is ready to commit, is actually going to keep the nexus lock until here, when also T1 is ready to commit. And that is going to guarantee that T3 is going to be serialized after the execution of T1 and T2, and at the same time that T1 and T2 can execute concurrently. So that's when it comes to cross-group. When it comes to in-group, what I'm trying to do is to increase in-group concurrency, so performance, while maintaining safety. And it turns out that one way in which people have been trying to do this is by, in the past, very, very creative. I don't know how many of you are familiar with this approach called transaction chopping. Transaction chopping is a very elegant thing. It says, you take your transaction, and then you do static analysis on these transactions. And you find out, provably, what is the finest automatic chopping that you can do of this transaction, such that the chopped system continues to be serializable. And it's provably optimal, okay? As truly beautiful. Okay? The only concern is that if I want to do, so the way in which transaction chopping works is you take your transaction, you express dependencies between operations within the same transaction, like these S edges, and conflicts across transaction as these C edges. And what you want to make sure is that there are no SC cycles. So you start with a very fine chopping, and then if you see that there is a cycle, you actually make the chopping coarser by bringing together, for instance, the top two red pieces, so that there is not going to be a cycle anymore, by doing something like this. Okay? So what is interesting is that what is nice about the notion of modular concurrency control is that the idea of actually applying techniques within the boundaries of a group can actually take techniques like this, and you can just apply them blindly on top of modular concurrency control to get a boost in performance that you wouldn't otherwise be able to get. The reason is, in traditional transaction chopping, you have to make sure that there is no cycle among all transactions. And as long as there is one cycle, you are in trouble. Here, because we are operating on a per group basis, the chances that there are going to be a cycle within each of the group is going to be much smaller, so you can actually chop much more finely. And in fact, it turns out that the approach is going to help also in that sense. One situation in which it's not going to help is if I have multiple instances of the same transaction running concurrently. In this case, I can take a transaction and another instance of the same transaction. I want to use transaction chopping, and I try to split them, and the only way to bring them together is basically to reconnect the whole thing as originally. And so transaction chopping doesn't help at all in this setting. This is where we introduce a technique that we call runtime pipelining. And runtime pipelining looks at that graph and actually makes the observation that if there is a dependency that is generated between the top two operations there, once that dependency is generated, these edges that used to be non-directional edges suddenly become directional edges. And if they are directional edges, if I want to avoid cycles, all I have to do is to make sure that the other cross edges are going to be in the same direction. And then there are going to be no cycles. And that allows me then to take something that otherwise I would have to execute sequentially and actually execute it in a pipeline fashion, right? And we're going to be able to get significant performance from it. And I'm going to skip the fact that we can generalize all of this. And I'm going to also skip the fact that I would describe to you how to group these things. And if you want, we can talk afterwards. I just want to show you to finish how it works, how well it works. And there are a bunch of operations, a bunch of questions that you can ask. The only question that I'm going to ask here is end-to-end performance. Okay? And here is the answer for TPCC and Fusion Ticket. And we are comparing Callus also with SALT, the system that you saw before. And let's look at these graphs in a little more detail. The first thing to observe is that Callus, remember, Callus requires nothing of the programmer. Okay? You take your application, you don't change a line, and you press a button, and the system does its magic, and then it's going to run like this. And you can see that there is a not insignificant gain. And if you look at where that gain comes from, you can see that you look at different components. You can see, for instance, what I get by just running transaction chopping instead of my SQL cluster. And you see that for some application, transaction chopping helps, TPCC. For some application, it doesn't help at all. If you take transaction chopping and you implement it in the context of modular concurrency control, you see that where it helps even more. And where it didn't help, now it can help quite a bit. If instead of simply using 20-year-old technique like transaction chopping, you add ideas like runtime pipelining and other optimizations that we have in our paper, you can see that you can get a further boost in performance. And what is remarkable is that we are something like within 5% of what we were able to get with SALT. The difference is that with SALT, we had to deal with the complexity of basify. Here, none at all. From the programmer perspective, nothing has changed. OK, that's what I wanted to talk about. And in conclusion, we talked about these two systems, SALT and Callus. SALT is based on this idea of the SALT isolation that provides a different perspective on the granularity of isolation to different groups of transactions. And Callus instead has this idea of modular concurrency control that we have further expanded in other papers that I'm not going to be telling you about. And as far as our friend is concerned, well, one can always hope that he's now gone free. Not really, but OK. So that's what I have to say. Thank you for having patience.